Hello everyone, welcome to IIT and Gate classes. I'm Mukesh Kumar and I teach here Signal System and Communication System. So today we'll be going through the amplitude modulation topic of the communication system and why we do the modulation. So first start with the uh, its syllabus. So it has four parts. One is analog communication, digital communication, random process, and information theory and coding. So analog communication, we have all type of analog communication like amplitude, phase, and frequency, and then we have some block level uh, amplitude or architecture of the communication system like super heterodyne receiver, and then we have a digital communication where we will go through the basic all the digital communication. Modulation technique that we use like PSK, SK, FSK, and QAM map. And then we will go through the random process. So random process, here we will use some probability theory and all to discuss this random process topic. And then last topic is the information theory and coding. Okay, so here the basic requirement for this analog and digital communication is to know the signal and system, and for the random process you should know the probability as well as the signal and system. Okay, so first let's go through what is the communication system. So this is how the typical block diagram of a communication system look like. So here we have a message signal that can be my audio signal, it can be some image, or it can be other electrical signal directly. Okay, so here if signal is not in the electrical form, first we need to convert it to the electrical form. So that is done by this input transducer. So this input transducer will convert that okay, highlight, okay, will convert that non-electrical signal into the electrical signal, and then we will give this electrical signal to the transmitter will process that electrical signal to convert it into another electrical form such that it is suitable for the transmission. Okay, and then it will pass through the channel. A channel is nothing but a medium over which signal will travel. It can be wireless or wired. Uh, when it comes to wired, it can be twisted pair, it can be coaxial cable, okay, so, and so on. So that is the channel. Channel is the medium over which your signal will be traveling to reach the receiver. Now, once it has traveled, it will reach to the receiver. Now, at the receiver side, we have a block called receiver, which will do the operation just opposite of the transmitter to get back the this electrical signal which is the input signal. So it will do the just opposite operation of the transmitter and will get a output signal which is same as the input signal. And then after output getting this signal, we will do the opposite operation what this transducer was doing. So this transducer was converting the non-electrical signal to electrical signal. Here we will convert the electrical signal to non-electrical signal. So if this was audio, this has to be audio signal. Okay, so this is the complete communication system. Now here one more block is there, distortion as noise. So this distortion as noise is like thermal noise of the devices, or it can be channel distortion, and it can be some random no distortion getting added to the channel. So that we will discuss in the random process and the random variable. Okay, then here we will always use a term called modulation. Okay, so modulation is a process of converting a low frequency signal to a high frequency signal. Okay, now why there is a need to convert a low frequency signal to a high frequency signal? Generally whatever we speak, or uh, whatever the signal that is at the input source will be a low pass in nature. For example, our audio signal is in the range of 20 hertz to 20 kilohertz, which is very less. Okay, this signal, if we want to transmit through a wireless channel, in that case the antenna that we have to use to radiate that signal, it will be very high, because the size of the antenna depends upon the wavelength of the signal or the frequency of the signal. So if signal frequency is very less, then its wavelength will be very high, and if its wavelength is very high, then its size of the antenna will be very high. For example, for the signal which have uh, band frequency around 3 kilohertz, its wavelength will be 100 kilometer, and the size of antenna will be in orders of some few kilometers. Okay, and that is very huge number. We cannot design that kind of antenna which has a kilometer in size. So here we need to, what we need to do, we need to do a modulation, which is essentially a process in which we convert a low frequency signal into a high frequency signal. So once we convert this low frequency signal into a high frequency signal, now the signal is at the high frequency, so its wavelength will be less, so the size of antenna will also go down. So this is the benefit of the modulation, but inherently there are some other benefit that comes into picture. So next is the interference. So let's say I have a three user and three receiver. Okay, three receiver and three transmitter. Three transmitter are transmitting signal x of omega, y of omega, and z of omega. They are in the frequency domain. In time domain, they will be xt, yt, and zt. Okay. Now this is the signal. These are the baseband signal. Let's say. Okay. Now I want this all of the signal to be transmitted through a same channel. So it means that I have to add all of them and send through the same channel. Okay. Once I add all of them, it will look like this, right? Once they reach the receiver for the user one, receiver will receive this signal. Okay. But from this signal, he want to get back to this signal, the user for user one. But he cannot get back this signal because here it got interfered by y and z. Okay, y and z are interfering with x, and because of that, user 1 will not get back to x of omega. Similarly, user 1 will not get back to y of omega, and user 3 will not get back to z of omega, because all these three are interfering with each other. Okay, but here we have not done any modulation. We are just taking the baseband signal or message which was at the input source and directly transmitting through one channel. But what will happen if we do the modulation? So let's say we are doing the modulation of x of omega, y of omega, and z of omega. So as I told, the modulation is nothing but a shifting low frequency signal to high frequency signal. So I have taken this x of omega from baseband and have shifted it to high frequency. Similarly, here I have taken y of omega and shifted it from baseband to high frequency, and z of omega from baseband to this high frequency. So whenever you are doing this shifting, it has to be done in such a way that this signal doesn't overlap with this signal and this signal doesn't overlap with this signal, or it essentially means that the shifting that I'm doing for the x of omega should not be same as y of omega. Okay, so here we are doing the modulation, and at the same time modulated frequency or the shifting frequency is different for all of them. Okay, and since shifting frequency is different for all of three, once we add this three, they will not overlap with each other. Okay, now they are not overlapping with each other, so we can easily get back to the user one by filtering this signal. Okay, so I will use a band pass filter and reject this too. For the user 2, I will use the bandpass filter which looks like this and filter out this too. And then I will use, for user 3, I will use this kind of bandpass filter and filter out this too. So again, with the help of modulation, I'm able to transmit multiple signal in a single channel. Okay, this is also called the frequency division multiplexing. Okay, now let's come to the analog modulation. So here, as I told, modulation is nothing but a shifting it. Okay, shifting in the frequency domain. Now to shift it, we use something called a carrier. So we use a signal called a carrier signal So the carrier signal here can be cos omega ct or sin omega ct. Okay, so we use this carrier signal that will help us in the modulation. Now in the case of amplitude modulation, so angle modulation will have a multiple type. One is amplitude, second is angle. And now again angle will have two type, frequency and the phase, that we will see later. Now come to the amplitude modulation. This is called the amplitude modulation because it is modulating the amplitude of the carrier. So we had a carrier which as of now it has a fixed amplitude, that was 1. Okay, but with the help of a message, I will generate a signal AT which will modulate the carrier. So it is a function of the message. So this is called the amplitude modulation because it is changing the amplitude of the carrier. Now in the case of angle modulation, here phi t will be a function of message. So here this phi t will be changing the angle of the cos omega ct. This is the angle term, right? So here this is called the angle modulation because it message is modulating the angle of the carrier. Here message is modulating the amplitude of the carrier. Okay, now let's go to the amplitude modulation, how the amplitude modulation looks like. So amplitude modulation is generally given as a plus mt cos omega ct. So this a plus mt is the amplitude of the cos omega ct, which is a carrier. So you see this uh, amplitude of the cos omega ct is a function of message, where mt is a desired message that we want to send to the receiver. Okay, so here this is the general expression of the amplitude modulation, or you can write it like this: a cos omega ct plus mt cos omega ct. And here this omega c or fc is generally very high, and it is much more than the bandwidth of the message signal. Okay, now let's come to the signal xt and let's see how it looks like. So let's say we have a mt, which is a message signal which looks like this. After that we have to add a. So I have added a, and because of that it has shifted up. So this is a plus mt. Now based on the what is the value of a, it can be shifted up more or it can be shifted up less. So here a value of a is very less, so it has not shifted much, but here value of a is very high, so it has shifted too much. Okay, now after that I am multiplying this with cos omega ct. Okay, so once you multiply with cos omega ct, it is nothing but a signal which is a cosine signal with this as an amplitude. Okay, so this is a cosine signal. So you see the solid line here, that is the complete a plus mt cos omega ct signal. So this is a cos signal whose amplitude is getting varied with time, because here mt is varying with time, and this is mt. Okay, now one important thing to notice is that if you see this dotted line, this dotted line is called the envelope, and generally we measure the envelope only for the positive value, we don't go for the negative value. Okay, so here when we want to recover the message, we track this envelope of this complete modulated signal to recover the message. Okay, so at the receiver side, we use something called envelope detector to recover this message, that we will see later what is the envelope detector. Okay, so as of now, just remember that this envelope detector is something which detect the amplitude of the a plus mt cos omega ct. Okay, and it works only for the positive value of a plus mt cos omega ct, not for the negative value. Okay, now let's take this case. In this case it is crossing the zero, so it has negative value also. So in this case, if you see this signal, it looks like this. So again in this case, this cos omega ct is where its amplitude is varying with time because of a plus mt. Now you see here, now here there is some interesting thing happening. Here our envelope is crossing, going down. Okay, here this envelope is going below zero. Okay, so if you see, this will be the, this solid line will be the our signal, and its envelope will look like this and then go up. Okay, because as I told, envelope we measure only for the positive value, so its envelope will be this dashed line, and instead of going down it will be going up. So you see here, in this case when we use the envelope detector, we will be able to recover the message. But in this case, when we try to recover the message with the help of another detector, we will recover this dashed line. Okay, so which is not same as this a plus empty. A plus empty was continuously going down, but here a plus empty went down, then again went up because of this zero crossing. So since here this envelope is not same as a plus empty, in this case we will not be able to recover our original message. Okay, since we are not able to recover our original message, this is undesirable. Okay, so we don't want this a plus empty to ever be negative. So a plus empty should always be positive for us to recover the message signal. So that is a very important criteria of the amplitude modulation. So a plus empty should always be greater than such so that its envelope is always a positive, and envelope detector can be used to detect the signal. Okay, so now let's come to the topic called modulation index. So first let's assume that there is a signal which is empty, and its maximum and minimum value is given as plus MP and minus MP. Okay, so the minimum value of empty will be minus MP. Okay, now a plus empty has to be greater than 0 for all kind of empty, whether it doesn't matter whether empty is positive or negative, it has to be greater than always. So the worst case will be when empty is minimum. Okay, so for minimum value of empty, this identity should still follow. Okay, so it means that a minus MP should always be greater than equal to 0. Okay, so if this thing is following, our a plus empty will always be greater than 0 because rest of the empty will always be greater than minus MP. So a minus MP should always be greater than equal to 0, or a should be greater than MP, or MP upon a should be less than equal to 1. Okay, so this MP upon a is called the modulation index. Okay, so since this MP upon a is always less than equal to 1, so mu should be less than equal to 1 but greater than e- 0. Okay, this is the criteria for the modulation index. And if mu is greater than 0, this is called the over modulation. This is nothing but this case in which it is crossing the 0. So if mu is greater than 1, this is called the over modulation. And in this case, that we will not be able to recover the message. So this over modulation case is undesirable case. So we don't want this to happen. So mu should always be greater than equal to 0 but less than 1. Okay. Now, in the last slide, we have assumed that the minimum value of message and the maximum value of a message has same magnitude, that is MP. Okay. So here, uh, let's take the case when minimum value and maximum value has different magnitude. Okay. So in the last case, we have assumed that M max is equal to minus M min. So both have same magnitude. Okay. But in this case, this is not the case. If this is not the case, in that case, we need to use this as a modulation index. Okay, this is general case of the modulation index. Okay, so here this is the M max, this is the M minimum, this is 2a plus M max minus M minimum. Okay, now if you see this formula, and if in this case, if you apply the last slide case, that is M max is equals to minus M min equal to MP. Okay, let's put it here. What will be happening to you? It will become mx will become mp, and minus m minimum will become again mp upon 2a plus mp and minus mp. So this two will cancel out each other. This will become 2mp upon 2a. So this will become MP upon A. So this is the same as the what we have seen in the last class. So last class is a special case in which Mx is equal to minus M minimum. And this is used in general. So this is a general case to use. So this should be the formula to calculate the modulation index mu. Okay. Now let's take an example. So here we have a given a message signal MT, which is this one, and we have a carrier which is this one. Now we need to find out which of the following signal is the AM signal without over modulation. Okay, So we know that AM signal looks something like this: A cos omega ct plus MT cos omega ct. Okay, and for this to be not over modulated, A plus MT should be greater than equal to 0, or simply saying this envelope should always be greater than equal to 0. Now this is the form of the AM, but you see the first option is not in this form. It has just one term, AC MT cos omega ct. So this is not the AM signal. Now let's come to the second case. Second case is in this form, but here let's see if this is following this criteria or not. So we have AC plus 1 plus MT. Okay, so it has envelope which is equal to AC into 1 plus MT. So envelope is AC into 1 plus MT. This should be always greater than equal to 0. Now put the minimum value of MT here and see if this is following this thing. So minimum value of MT is minus 2 here, right? So here M minimum is minus 2. So let's put it here. It will be AC 1 minus 2 greater than equal to 0. So this will become minus AC greater than equal to 0, and this is not possible. So since this is not greater than 0, this is not following this property, this will not be a AM signal without over modulation. Here there is a over modulation. Now let's go to the third case. Again, third case is in this form, and let's see what is the envelope. So here let's take the cos omega ct common. So it will be AC plus 1 by 4 ACMT cos omega ct. Okay, and this is the envelope. Let's see if envelope is always greater than 0. So again we will put MT equal to minimum or value of MT. So AC plus 1 by 4 AC into minus 2 greater than equal to 0. This will come out to be 1 by 2 AC. See, this is always greater than equal to 0, right? So it means that this is following so this is in the same form, and it is also following that envelope of a signal is greater than equal to 0. This is the correct answer. Okay, and if you see this last one, this is not in this form. It has message into cos plus message into this is not a even message. It is a sine to pi fmt plus sine to pi fct, and we don't have any term in this amplitude modulation. So this is not a AM signal. So the correct answer is this one. So if any signal is given and you are asked to find out whether the signal is AM or not, so first thing is to check whether this is in this form or not, and second thing is to check whether there is a over modulation or not. Okay. Now let's go to the power efficiency. So here, if you carefully see this modulated signal, okay, here we have A cos omega ct and MT cos omega ct. So only one term contain the message. This term doesn't contain the message. So this term is kind of redundant term. Okay, this is not useful term at the receiver. Only useful, not useful. Okay, this is not useful. Only this is useful. Okay, so our efficiency is given by useful power upon total power. Total power is the total power of this complete signal xt, and the useful power is the power of mt cos omega ct. Okay, now let's calculate the power of a cos omega ct. So we know that power of any cos omega t is nothing but a square by 2. So for a cos omega ct, it will come out to be a square by 2. Now power of mt cos omega ct will be m square dash by 2, where m square dash is mean square value. Okay, now here if you put this power and this power in this formula, so the useful power is only this one, which is a pm, and total power is power of pm, that is message power, and carrier power, that is pc. So this is the efficiency. When you put this pm equal to m square dash by 2 and pc equal to a square by 2, you will reach here. Okay, Now this is the efficiency term. Okay, now let's take a special case when the signal is a single tone. When we say single tone, it has a single frequency. Okay, tone modulation. In this case, the mean square value of the message is given as am square by 2. Okay, everyone knows that this is the mean square value for any cos. So for a cos omega t, we know that root mean square value is a by root 2. So mean square value will be simply the square of this, that is a square by 2, and in this case a is nothing but am, so it will be am square by 2. Now let's put it here in this equation. So it will be am square by 2, am square by 2 plus a square, or you can write it something like this. So that is am square by am square plus 2a square. Now we also know that mu is mp upon a for the symmetry signal uh, which has positive and magnitude. This m mean and m max has same magnitude. So again, in this case, m mean is minus am and m max is am. Okay, so m mean is minus am, m max is plus am. So both are same magnitude, so we can use this formula for the mu. So mu is given as mp upon a, and mp is nothing but am upon a. Okay, now let's take this formula and divide both numerator and denominator by a square. Okay, you see it is am square by a square. We know that am upon a is mu, so you can write this as a mu square. Again, this is am square by a square, mu square, and this will be 2a square by a square. So a square will cancel it. We will be just left with 2. So this is the formula for efficiency, which we have written here. Now you see, we know that mu should always be less than equal to 1. Okay, so when you put mu equal to 1 here, you will get 1 by 3. So efficiency will always be less than equal to 3, or maximum efficiency is always 1 by 3 or 33% for the AM modulation, which is very less. Okay, so this is the efficiency of the maximum efficiency of the AM modulation. Okay. Now let's take a problem. Here our message signal is given, and here the AM signal is given, and it is a1 plus mt cos omega ct, and we need to find out what is the power efficiency. So we know that what is the now this is not a single tone case because we have two tone, so we won't use the second formula which was in terms of mu. We will use a formula which was m square t dash, which is the mean square value of mt, m square t dash plus a square. Okay, this was for a plus mt cos omega ct. Okay, now a is nothing but 1 here. A is equals to 1. Now what is the root mean square of value of mt? Mean square value of mt, that is, so if you have any signal which is summation of sinusoidal, let's say cos omega 1t plus a2 cos omega ct. So this you will see in this signaling system that whenever you have the summation of two signal and you want to find out what is the mean square value, it will be a1 square by 2 plus a2 square by 2 simply. Okay, summation of individual mean square. Okay, in this case we have a 2 cos, which is two sinusoidal signal. So one is zero point 0.5 cos omega 1t, one is minus zero point 0.5 cos omega 2t. So the mean square value will be 0.5 square by 2 plus 0.5 square by 2. Okay, you can write it as a minus 0.5 square by 2 because here it is minus 0.5, but ultimately it will result in plus. So this will be 1 by 8 plus 1 by 8, that is equals to 1 by 4. Okay, so let's put it here. It is 1 by 4 plus 1 by 4 plus 1, which is eta. It will be 1 by 5. So this is the efficiency, And in terms of percentage, you just multiply it by 100. That will be 20%. Okay, so in this case, the efficiency is only 20%. So this is the answer. Okay. Now let's go to the uh, spectrum of the AM signal. How does the spectrum of AM signal looks like? Okay, so first let's see again. This is the amplitude modulated signal, and let's assume that there is for the MT we have a Fourier transform MF which looks like this. It can be in any form. Here I have taken as a triangle. It can be any shape, in any shape. Okay, so the Fourier transform of MT is M of F, and we need to find out what is the Fourier transform of X of T, or the spectrum of AM. So here MT cos omega ct, if you take its Fourier transform, it will be like this. Okay, so here again, this I have taken from the signal and system. So whenever there is a signal MT, you multiply it with cos omega ct, its Fourier transform will be shifted version of M. So 1 by 2 mf minus fc plus m f plus fc. Okay, that's what I have written here. Okay, and also for a cos omega ct, this will be the Fourier transform. Actually, this will be this will be a by 2 del f minus fc and del a f plus fc. Okay, so this is the mf. Now to get this Fourier transform of this signal, we if you want to plot it, first we need to this shift this mf by fc and then minus fc. So once we need to shift it left, and once we need to shift it right. Okay, so this is shifting right and this is shifting left. So let's take this and shift it right by fc. So when you shift this right by fc, this is a zero frequency, it will go to the fc. This is plus b, this will go to fc plus b, and this is minus b, this is will go to fc minus b. Okay, so this is this term, and also there is a 1 by 2 term. So whatever the value was there, let's say some value here, this value will be half of that, because there is a 1 by 2 term here. Now similarly this m plus fc, we are shifting m left by fc. So the same operation we are applying for shifting it left. So whatever the signal is at 0 will go to the minus fc, and this plus b will go to fc minus b, and this minus b will go to minus fc minus b. Okay, so this is how the spectrum of this one will look like. Okay, now let's take the second one, which is a by 2 del f minus fc del f plus fc. So it is nothing but a two impulse. One is located at fc, one is located at minus fc. So these are two impulse. Okay, so one is this one and one is this one. It is located at fc and this is located at minus fc. Okay, so this is how the total spectrum. So this is the spectrum of am. So this complete thing is a spectrum of am, which has this term because of the message, and it has impulse because of the carrier term, which is a cos omega ct. Okay, now in this complete thing, there's something called upper sideband and the lower sideband. Okay, so this thing which is left of the fc is called the lower sideband, and which is right of the fc is called the upper sideband. So this is lower sideband, this is upper sideband. Now in the case of negative one, the thing which is right of the minus fc is called the lower sideband, and thing which is on the left of the minus fc is called the upper sideband. Okay, so this and this are upper sideband, and this triangle are lower sideband. Okay, so now let's come to the bandwidth. So you see here, so bandwidth of any signal is uh, if you want to calculate the bandwidth of any signal, it is nothing but a frequency range over which it is non-zero. So here in this case, it is non-zero from 0 to b. We will just take the positive. We don't take the negative when we calculate the bandwidth. So here the bandwidth of this signal is b. Okay, so the message signal bandwidth is b. Now when we are shifting it right, you see this is the positive frequency that we are getting, signal at the positive frequency. And what is the duration of this frequency? It is from fc minus b to fc plus b, and if you calculate this width, it will be 2b. So if there is any signal which has massive signal which has bandwidth b, when you modulate it after the modulation, its bandwidth will be 2b. Okay, that is one important thing in the amplitude modulation. Bandwidth will get doubled in the amplitude modulation. So bandwidth is always given as a frequency range over which signal is non-zero. Okay, and it is calculated only for the positive frequency. So here I have taken it from 0 to b, and here it will be fc minus b to fc plus b. Okay, so that's all about the amplitude modulation. See you guys in the next class.